Resonance in series RLC circuits. What the heck is resonance? Huh, so glad you asked. Let's discuss it, shall we? Resonance is a fancy word to describe a bad situation. This is a resonant series RLC circuit. What resonance indicates is that we have reached a point where the power factor of this circuit is equal to, well, what is it equal to? We've got 20 ohms of XL, 20 ohms of XC, we've got 2 amps worth of current and a 1 ohm resistor. That means that when I do an impedance triangle for it, I get a Z total of 1, and if I wanted to calculate the power factor of the entire circuit, it would also be 1, because the resistance and the impedance are identical. So a power factor of 1, what does that mean? Well, even if we were to calculate with the power values in here, P 4 watts, 80 VARs, 80 VARs, we still get a value here of 4 VA. And so again, still, we have a power factor of 1. But why is this poor or bad? What do we consider bad? Well, it's a funny situation because really, if you look at this circuit, what is the only component that's restricting the total current of the circuit? What is the only thing that's offering an opposition? And that one object that's offering an opposition to the current is actually this, the 1 ohm resistor. The 1 ohm resistor is the only item that is impeding or slowing that current value, whatever voltage source it happens to be. What if the resistor was only 0.0001 of an ohm, as in a conductor? What would happen to the total current if it was only 0.0001? Wouldn't the current be really high? And it would. It would be a bad situation. And at times within design of larger systems, the conductors themselves pose a little bit of resistance. They are also typically coupled capacitively to ground, which is not really an intention, but an outcome of using AC. And due to the electromagnetic flux, they do possess a certain amount of inductance. So it's an interesting scenario. Now, to get the full effect of what's going to happen in this circuit, let's take this particular circuit and just add some basic questions. So here it is again, 1 ohm resistor, 20 ohm XL, pure inductor, 20 ohm capacitor, 2 amps worth of current flow. So what would happen to the total current if I increased the XL? If I increase the XL of the inductor, what's going to happen to the current in the circuit, the 2 amps? Is the 2 amps going to get larger, or is it going to get smaller, or would it just stay the same? So if I increase the XL, what's that going to do to my impedance triangle? Wouldn't that actually make a bit of an impedance triangle? Because if I increase the XL, these two would no longer be equivalent, would they? And so the power, or rather the impedance triangle, would look, instead of like a horizontal line, which is what it is on the previous page, it would look a little bit like this. And so I would have a net value of X. R would remain the same, and Z, what would happen to Z? Z would go up. If Z total goes up, what happens to the total current? The total current would go down. The total current would go down. Okay, well, that makes sense. Let's see what would happen if we were instead going to increase the capacitive reactance of the capacitor. Well, all right, well, we still have a impedance triangle that's horizontal. What would happen to the overall net? If this increased in value, then wouldn't we have a net value of reactance? The answer is yeah, you would. Resistance would remain the same, but the Z total would again increase. So what would happen to I total? Well, it would go down, wouldn't it? Okay, so that makes sense. What then happens if we choose instead to simply take out or lower. Let's lower it instead. Okay, let's see if we get a different outcome. I'm going to lower the XL value of the inductor. What's going to happen? Are we going to have a net value of impedance here? So there's my impedance triangle. Up here, we had more XL. Over here, we had more XC. What about this one here? I mean, if I lower the XL to say 15, which one of these two is going to be larger? The XC is going to be larger. So you'd end up with XC net. Resistance would remain the same. What happens to the Z total? Z total would increase. Oh, this is getting repetitive. What would happen to the current then? It would have to get lower. Okay, well, you tricked me 3 times. Let's try the 4th. This has got to be different. What if instead we decrease the capacitive reactance? If we decrease this value to say 15, then this would be larger and there would be an excess or an overall net of XL. So we'd have XL net. Resistance would remain the same. Z total would, oh my goodness, it would actually go up, wouldn't it? So that would mean that the total current would, oh, that would go down. Okay, so we take it to an extreme level. What would happen if I just remove the inductor? I'm so sick of this discussion. Let's just get it out of here. If I remove the inductor, then all I'm left with is the capacitor. So that would actually have a significant effect overall, right? Because that would mean that my inductor being absent, I would have a significant amount of XC. And so the XC value would actually be quite a bit larger. I mean, can't even really see it, but we would have XC here, R, and Z total. That would make a really big increase to Z total and a really sharp decrease in the current. Okay, final one. Guess what would happen if you remove the capacitor? And that's right. The total impedance would go up and the total current would go down. So this is a weird situation. It doesn't matter what you do in a series resonant circuit, any change to the properties of this circuit will cause the total impedance to increase and the total current to decrease. Weird outcome, eh? It's a bizarre situation with series resonant circuits.